Coming up next on Futures in Biotech, Professor Jeffrey Hangst explains how he and the Alpha Collaboration team members have successfully trapped anti-hydrogen to hopefully answer some of the most important questions about the nature of our universe.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Futures in Biotech is provided by Cachefly at cachefly.com.
This is Futures in Biotech, episode 87, Antimatter Message in a Magnetic Bottle.
I believe that biotech is the next frontier.
Probably the greatest intellectual revolution that's ever taken place in man's history. DNA is the code for life. We're actually beginning to understand how life works, which I think is something that's mind-blowing in and of itself.
There was going to be a genetic component to aging.
How long was the extension?
About 30-40%. For humans, that would equate to something like 20 to 30 years.
How close are we to actually having a therapeutic?
Ballpark, 10 years.
Potentially one of the things that'll end up rocking the world the same way that people said, oh, the sun's the center of the universe, oh, this and that and everything. And now here's somebody who can come out and say, hey, look, here's how we compare it to our closest evolutionary relative.
Welcome to Futures in Biotech. I'm Marc Pelletier. Today, we are very, very fortunate to have a great guest. He's doing some incredible work, and so it's not so much biotech, but it is fundamental to who we are and where we're going. And what a great opportunity to get a first-hand account from him about his work. He graduated from MIT for his undergraduate and master's, received a PhD from the University of Chicago from work done at the Fermilab and the Argonne National Laboratory. In 1994, he moved to Aarhus University in Denmark and received the European Physical Society's 1996 Accelerator Award for a Young Scientist for his work on laser cooling of stored ion beams in the Astrid storage ring in Aarhus. He was then stationed at CERN full-time as of 2001, was a founding member of the Athena Anti-Hydrogen Collaboration, and was the physics coordinator of the experiment that produced the first cold anti-hydrogen atoms at CERN Antiproton Decelerator in 2002. He then founded the Alpha Collaboration, which first demonstrated trapping of anti-hydrogen atoms in 2010, for which he was awarded the 2011 John Dawson Award for Excellence in Plasma Physics Research. As a matter of fact, on Futures in Biotech last December, we selected that paper as one of the papers of the year. And even though it wasn't biotech, we just could not ignore it. It was undeniably one of the most fascinating papers, probably of the decade, in my opinion. So I'd like to welcome Professor Jeffrey Hangst. Welcome to Futures in Biotech.
Thank you very much, Marc. It's a pleasure to be here.
Let's start the show off, if we can, to find out a little bit more about you, so that we know the context of your work and how you came about it. Because this is some complicated material, so let's start with the easy stuff. Tell us a little bit about your early scientific studies at the University of Chicago, and sort of what got you going. What were the first questions? How you got into your area of research?
Well, when I was at Chicago, I was also working at the Fermi National Accelerator Lab, working on antiprotons. As you know, Fermilab uses antiprotons in collision with protons at very high energy to look for new things. In fact, it's a kind of a historic day because today is the last day of operation of the Tevatron, the machine that brought me to Fermilab in Chicago back in the early 80s. So I was interested in accelerators, interested in antimatter. I did my PhD while I was at Fermilab and hooked up with some people in Denmark who were doing sort of atomic physics with accelerators, and went there with also the intention of working with some people at CERN. The difference between Fermilab and CERN at that point was that CERN had a program with low energy antimatter. Fermilab chose not to pursue that. I got very interested in anti-hydrogen and the possibility of making anti-hydrogen. And so I decided to relocate to Europe to pursue that and some other areas of research.
What What was it about antimatter that piqued your curiosity?
Well, the interesting thing about antimatter is its absence. As soon as you realize that, as far as we know, half the universe has gone missing, you can't help but be fascinated by that. Science fiction or no science fiction, that's just intriguing. And I think anytime we can get our hands on some antimatter, we should study it and see what's going on. So a lot of people will say that the interest in antimatter is because of science fiction, but when you talk to students about it, you see the light go on in their head and say, wow, this isn't science fiction, this is real. This is something that's really fascinating. And I still feel that way. I think it's just really cool.
Half the universe. Okay, so now that raises the big question is, oh my God, half the universe is gone. We're doomed. Not only doomed,
it's the opposite of it. If it weren't gone, we wouldn't be here.
Right. Oh, then phew. Okay. Wow. That half the universe is gone. Is it gone missing? Well, look, before we get to that, so maybe you could explain a little bit what antimatter is, maybe the anti-particles, and then the anti-atoms. And so get an understanding of this. Because as I said, I'm a molecular biologist. I stop at the molecule. So maybe.
Okay, we have to go back to the 1920s. The English theoretical physicist Paul Dirac. He was working on an equation to kind of unify relativity and quantum mechanics. And he hit upon an equation that had some solutions that he couldn't explain. The solutions would correspond to things with negative energy. Now, 99.99% of all scientists in the world would have thrown that equation away because it looks faulted. Dirac kind of invented thinking outside the box and said, my equation is right. These solutions correspond to something we haven't seen yet. And those solutions are antiparticles. Now, just a few years later, people discovered in cosmic rays the antiparticle of the electron. We call it the positron. Now we understand that every particle, fundamental particle that we can make or observe has an antimatter equivalent. So that's a particle that has equal but opposite properties, if you will, the same mass, opposite charge, and so on. So that's just how nature is. There are pairs of these things. In fact, if you make things in the laboratory, and here's a good one, E equals mc squared, right, is the most famous equation in all of physics. Mm-hmm. What it means is that if you have some energy E, you can make mass m, and c is the speed of light. So in CERN, we're in the business of using E to make m. And every time you use energy to make mass, you make matter and antimatter. That's a natural law.
You know, people tell me that, you know, oh, Marc, you're going to create a monster in the lab, right? But so I'm not creating anything from scratch. I'm manipulating, but I'm not creating things from scratch. I guess you aren't either. You're taking energy, so it's not creating it from scratch. But so I want to know a little bit more about how Dirac, if you know, so he proposed the mathematical equation that suggested that there was a negative energy, and that when was it first demonstrated? When were the first antiparticles seen? So in like 1932, if I remember correctly, it was just a few years after his equation. Anderson saw positrons in cosmic rays and confirmed that there was an antiparticle to the electron. So it went very quickly. Wow. So physics really, I mean, you know, the molecular the atomic physics, really ahead of the game, ahead of the curve versus, you know, all other aspects of life sciences. And wow, it's just amazing. 1932, an experimental validation of Paul Dirac's equation. That's right. Good job, guys. Wow, that's nuts. Okay, so then you say every particle that you make has an antiparticle. So maybe, do I want to get into the techniques? So maybe you could explain the nature of that. So for every atom that we are, there was some antimatter. Every atom that I guess makes us, or everything around us, our universe, there was an antimatter component to it.
Well, that's perhaps the biggest open question about how the universe evolved. When we make matter in the laboratory using energy, we always get equal amounts of matter and antimatter. So if the laws of nature are really universal, then at the time of the Big Bang, this big explosion, this singularity of energy that created the universe, there should have been equal parts of matter and antimatter. That's what the natural law, as we understand it, says. What we don't understand is what happened to the antimatter. It's clear that matter and antimatter can't coexist, right? That Star Trek got that part of it right. If you mix them, they annihilate each other and they release a lot of energy. The most energy per capita that you can get in the universe. So
really, wow.
Yeah, I mean, it's the mass just disappears and it's completely converted to energy. If you compare that to burning something or even a nuclear fission reaction, it's just much more efficient. Everything is converted initially to energy. So that's why this stuff is in the lore of science fiction. It's the ultimate energy source. If you had some, someone gave you some.
How much does it cost to make? I mean, in terms of energy production, do you get, say you put in a certain number of watts of energy or do you recover it at 100%? So is it sort of equal, or is there a huge loss?
That it is incredibly inefficient to make antimatter. It uses much more energy than you would ever get out. It's a complete loser as an energy source. This is where the science fiction breaks down. It's just the exactly wrong thing to do if you're trying to make energy, right? An energy source should just be there and give you energy for nothing, like oil does or like coal does. We must first create antimatter, and it takes infinitely more energy. It's embarrassing to quantify it, so I won't even do it. The other problem with this is that, say you wanted to make just a gram of antihydrogen. That's what Dan Brown had in his book, right? That would take you longer than the known age of the universe with the techniques that we have today. So you don't need to worry about this. This is not really an issue. But the question, the intriguing one, is still there. What happened to the antimatter? The laws of physics as we know them say that antimatter and matter should behave in the same way. But obviously they don't, and we're trying to figure out why.
So at the Big Bang, was the Big Bang an annihilation
the Big
all
Bang,
the matter of the universe? Or?
Well, who knows what came before the Big Bang, but the Big Bang, as we understand it, was a huge amount of energy being released throughout space. This energy created mass, it created particles, and the whole thing cooled and expanded. Now, again, at the instant when all that energy appeared, it would have converted into equal amounts of matter and antimatter. But it's like nature took a left turn and said, okay, we can't have both of these things in the same space. We're going to choose matter. Nobody knows why that choice was made.
At the Big Bang, those first particles that were made, were they, was it a plethora of different levels of atoms, like a supernova, or was it subatomic particles?
There's a whole history of how things evolved and cooled in the Big Bang, and it would take us a long time to discuss it. Okay. It's really not my area of expertise. I'd probably get it wrong. So
sure,
let's not go there.
It's okay. I don't know where. So we're kind of flying here, without a net.
I'm a humble experimentalist. I work in the lab, not in the imaginary world of the Big Bang.
Well, that's good because the lab is where all the fun happens. So let's any final so when you're looking at when you're predicting antimatter, I suppose, can you mathematically predict a lot of its properties, or is there enough data collected that gives you an idea of what it truly is, and if there's any kind of explanation as to why the universe took a left turn in that what we know mathematically? Are there predictions out there? Do you know what you're to expect?
Okay, well, since we've known about antimatter, every time we have a new bit of it, we study it to compare it to its matter twin. So, okay, that very basically, atoms are made of protons, neutrons, and electrons. We can have antiprotons, antineutrons, and anti-electrons, which are positrons. So people try to measure very, very precisely if a positron and electron have the same charge, for example, have the same mass. And those limits are improving all the time. People keep working at this because the difference may be very, very small. You know, whatever it caused the left turn, as we were talking, maybe in the 15th decimal place. You just don't know. So there's a whole history of people looking very precisely to compare particles of antimatter. And I'm distinguishing that because what we do is to work with atoms of antimatter. And that's only been possible since 2002, when we learned how to synthesize the simplest antimatter atom. That's antihydrogen. It's a number -1 on the periodic table, if you will. So
the negative.
That's the only... Yeah.
That's crazy. Yeah, I'm sorry. This is really neat stuff. I'm just trying to wrap my head around it. So the anti-periodic table that sheesh, God, this is really screwing up my training here, and it's going to have to drop my PhD.
So it's easy because it stops there. You don't have to worry about and we can't make it.
Yeah, and you made it, right? So you and your team, the Athena. Can you tell us a little bit about that first experiment, the first time you had a full anti-atom?
Okay, in Athena, which was the predecessor to Alpha, we learned how to mix clouds of antiprotons. Again, the reason we're at CERN is because they can make antiprotons. They have an accelerator that uses energy to make antiprotons. By the way, somebody won the Nobel Prize for just figuring out how to do that back in the early 80s. So there's a whole history of what you need to do to get antiprotons that precedes any of our work. So we're at CERN to get the antiprotons. They send some to us. We stop them and hold them in a kind of a electromagnetic bottle. The antimatter has
send
to
it
be
to you in a tube or in a flask?
No, it comes out of an accelerator at close to the speed of light in a kind of a bunch. You can imagine it's actually a bunch about 30 centimeters long. They send us one every 100 seconds, and it's got about 40 million particles in it, which sounds like a lot, but is nothing on a macroscopic scale. So we slow those down and stop them and cool them down. And then we do the same with some positrons. We get positrons from a radioactive source. You can, if you have the mad scientist license, you can buy a radioactive thing that just sits and emits positrons all day. And you can accumulate those. You make a cloud, again, in one of these electromagnetic bottles. And then you put them together. And in 2002, we learned how to do that in the Athena experiment, to mix these things to make antihydrogen, which is neutral, right? So one negative antiproton, a positive positron, they make an atom, which is the opposite of the hydrogen atom. And you can see that. In fact...
Where did the neutron? There's no neutron in hydrogen.
No, there's no neutron in hydrogen 1. You can have deuterium or tritium, which have neutrons, but we can't make those. Antihydrogen is the only antimatter atom we can imagine making with any kind of a number that would be useful for doing an experiment.
Well, let me ask you, let's break this down just a little bit. So this is in 2002. You've got a particle accelerator that's sending you 40 million antiprotons every 100 seconds, 30 centimeter cloud, I suppose. Where's the energy source for that? Where are we getting enough energy to create this? And what form of energy is it that is converted down to the antiproton?
Okay, so CERN has a chain of accelerators that go from zero energy up to some energy. They accelerate protons in this particular experiment. And then to make antiprotons, you run protons into a target at high energy. And they interact with the nuclei in the target and make a lot of junk. Some of the junk is antiprotons. The key then is to separate them from the other junk, store them in a machine, and actually slow them down. CERN has the only machine in the world that decelerates antimatter. We actually would like our antimatter to be at rest. We'd like to go from these speed of light situation to one where the stuff is just sort of quivering in our electromagnetic bottle. And that's the techniques that have been developed in the sort of last 20 years, how to go from something which must be created at high energy down to something that you can manipulate and use to form atoms. To form atoms, you want things to be cold. And by cold, we mean very close to absolute zero.
Do you freeze the magnets down? I mean, and first of all, does antimatter react to magnets the same way? Is the magnetic field of the protons, the antiprotons, are they repelled by our current magnets, or do you have to just switch the poles of the magnets? Is it magnets?
Yeah, we use magnets and electric fields to control these things. Antiprotons have the opposite charge of protons, so they behave like charged particles with the opposite charge. It's an unanswered question to how many decimal places the charge of the antiproton is the same as the charge of the proton. The standard model predicts they must be identical, but the limit of that measurement is like 10 to the minus 10, something like that now. So these are, in some sense, open questions, but for the bulk behavior, antiprotons behave like negative protons. So we just treat them like charged particles.
Like electrons.
In fact, we use electrons to help cool down the antiprotons. That's a technique that's very important. You can store antiprotons and electrons in kind of the same bottle, if you will, and they interact
repel each other?
colliding. They do, but okay, this we can talk about this. This is easy to understand, and it's kind of cool physics. If you put electrons in a big magnetic field, they go in circles, in spirals. And if you remember back to quantum mechanics, the problem with the original atomic theory was that people thought that electrons, when they're doing these circles or orbits in their atoms, would just radiate all their energy away and the atom would collapse. Right? That was the problem with the early, before quantum physics came along. So what Bohr did was explain that, okay, if you quantize electron motion, the atom doesn't collapse. So it is really true that if you put electrons in a big magnetic field and they spiral, they radiate away their energy. And so if this magnet is at 4 Kelvin, which is, liquid helium cooling temperatures, the electrons try to cool themselves down to 4 Kelvin. You just throw them in there, hold on to them, and they do this for free. Okay? That's because they're light particles. They have a small mass compared to the antiproton. The antiproton doesn't cool itself like that. But if you put antiprotons in a cloud with cold electrons, they cool themselves off by colliding with the electrons. Okay?
Mm-hmm.
So we use electrons to cool antiprotons in the initial state. After we've caught this cloud of rather high energy antiprotons, they're mixed with electrons, and the electrons kind of cool them down close to absolute zero.
Wow. So that makes a lot of sense. So you can cool them down with electrons. Electrons are nice at cooling if you put them in liquid hydrogen cooled magnets, I suppose. Are they like magnets that are in refrigeration units, or a lot of liquid hydrogen? Liquid helium. Liquid helium. So do you have a liquid? Yeah. Is this happening in liquid helium, or is the vacuum cooled down?
No, this is vacuum. This is probably the best laboratory vacuum you can create. It's a high vacuum to begin with, and then you cool it down, the walls of the vacuum apparatus down to 4 Kelvin. And everything that's not helium sticks to the wall. Right? It's so cold that it's called cryopumping. So you must have ultimate vacuum if you want to deal with antimatter, because if it meets some matter, it annihilates and you lose it. But we can hold on to antimatter particles for thousands of hours. Right? We have really essentially no chance of them running into matter in this vacuum. So the electrons cool themselves down and interact with the environment because they're charged. So they can cool down until something is trying to heat them up. We don't actually get all the way to 4 Kelvin. That's a little bit technical, but it's for free still. The electrons just radiate their energy away. The positrons, the anti-electrons, do the same thing. We put them in the magnetic field and they radiate their energy away, and you end up with very cold positrons.
Is this very similar to what a PET scanner would have? Well, PET scanner is positron emission tomography, right? So a PET scanner, positive electrons do the same thing? Do they like to be cooled? I mean, do they naturally cool?
Yeah, the positrons, if they're in a magnetic field, in vacuum, it's very important. They need to be in vacuum, otherwise they just hit matter and they annihilate. They will do the same thing. They have the same mass as electrons. It's about 2,000 times less than that of the proton, the antiproton. So they radiate their energy away very quickly in just a few seconds when we put them in the magnet. In the PET scanner, you actually have radioactive stuff in your body that's emitting positrons. Right? You're not actually injected with positrons. You're injected with some nucleus that can emit a positron. Then that positron annihilates in your body, and you look for the signal of the annihilation. We're working in vacuum, very, very high vacuum. We have no matter around.
So you're at a deeper vacuum than in space.
Absolutely.
Wow.
Space is full of junk.
Yeah, I'm trying to think of the experiments I've done with electron microscopes and trying to dry samples in cryovacs that drew a fairly strong vacuum, but it's nothing like what you guys have.
It's not within 6 orders of magnitude of what we do.
That's really neat. Cool. So the carpets are clean. Or you throw those on, nothing in the room. No air. Okay. So that's pretty neat. Let me figure out here. I'm trying to figure out how you separate your antiparticles from the junk. Well, some person's junk might be other person's, gold. So do you each share the various particles when you smash them really, really hard? Or
no.
Really throw out 90% of it and you take the negative protons?
Yeah, the antiprotons. This machine is only there to create and store antiprotons.
Okay.
So what happens when all the junk comes out of the target? You can use a magnet to select the mass that you want. So everything coming out goes through a magnet. They bend in different angles, and you just collect the stuff that corresponds to the antiproton angle. It's just a mass separator. The technique is used in many branches of physics and chemistry. So you just take the antiprotons, and you're not interested in anything else in this particular machine.
Somewhat like a mass spectrometer?
It's exactly a mass spectrometer for antiprotons.
I wonder how much one of those costs. Wow. Well, you have to ask the government, the governments. This is a multinational project to understand the universe. So I think it's not about the grants. It's about I guess you still have to write grants, right?
You do, yeah. I mean, we have to, we're publish or perish like everybody else. We have to come up with results regularly.
Yeah, to be able to purchase the next level of negative or anti-proton mass spectrometer.
And there's not much off-the-shelf stuff we can buy.
I bet you could whip one up on your bench, right? And you've got all the... Very few people can. So that's pretty amazing. So this is pretty much a description of the technologies to get to the 2002 level of antiproton collection used to mix with the positive electrons to create antimatter. But in 2002 versus 2010, where was the big leap in technology that allowed you to capture them? Should we show the slide, maybe? By the way?
Up to you.
We have a slide. The last photo on the website, Liz, this might actually help because it's it's basically the image you had in your paper of the anti-hydrogen trap.
Okay. Yes. Okay. Okay. What's different about the 2010 device, the Alpha device, and the Athena device? In Athena, when you make the anti-hydrogen, because you've combined a positive and a negative charge, you end up with something neutral. And the fields that you're using to hold the charged particles do nothing, because now it's neutral. It has no net charge. So it just flies off and hits some matter, which would be the yellow thing, the inside of the trap in the picture you're showing, the electrodes that make up the ion traps, and annihilates. In fact, that's how we show in Athena that we make antihydrogen. We actually just let it fly off, annihilate, and we detect the very characteristic signal of the annihilation. So what's new about Alpha is that we don't want to throw away this antimatter. Obviously, we want to study it. That's our long-term goal, is to check this stuff out and see if it's like hydrogen. So how do you hold on to something that's neutral? Right? That's the big problem. It turns out that although it's neutral, anti-hydrogen has a little bit of a magnetic character. You can think about it like a little compass needle that's flying along inside the atom. So if you have a very, very strong magnetic field, you can deflect this magnetic item. And the rub is that this interaction is extremely weak. Compared to trapping charged particles, this is extremely weak. Let me put it in numbers for you. When we catch the antiprotons from the antiproton decelerator, if you think about their energy in temperature units, it's tens of millions of degrees Kelvin. Okay? They're easy to catch. We use a few kilovolts on our trap, and we can hold those things that are incredibly hot. When the thing is neutral, when it's anti-hydrogen, the best trap that you can build, the deepest bowl, if you will, can only hold things that are 0.5 degrees above absolute zero. Okay, so the whole art of doing this experiment, of holding on to antihydrogen, was building the deepest possible magnetic bottle that we could make and making the coldest possible antihydrogen atoms that we could make so that they don't fly out of the bottle. Okay? Mm-hmm. So you can think of this, here's a good analogy. Imagine a marble in a bowl. Okay, a marble rolling back and forth in a bowl. If the marble goes too fast, it goes over the edge of the bowl and hops out. Okay? That energy of the marble is temperature to us, right? It's a kinetic energy of motion. So we build our antihydrogen marbles in a bowl. And if they're not moving too fast, they stay in the bowl. If they're moving too fast, if they're too hot, then they fly away and annihilate. Okay? The problem is that this is the world's shallowest bowl. It can only hold things that are moving very close to absolute zero temperatures. And that's kind of what took us in a nutshell from 2002 to 2010, was to learn how to build this thing and to make the cold atoms.
How do you cool the receptacle, the tube that detects the annihilations? Does it one detect the annihilations and two have a bifunctional also hold the field?
Okay, the yellow thing in the diagram that you showed has the electric fields to hold the charged particles. All this is in a big magnet. In fact, very similar to an MRI magnet that you would go and stick your head in the hospital to search for your brain. We have a very high field going along the axis of this device. The thing that actually makes the magnetic bowl are the red and the green coils. These are superconducting magnets, state-of-the-art, by the way, built in Brookhaven National Laboratory in the United States. Those are what form the magnetic bowl, if you will. And of course, all this is going on in the vacuum. Inside the yellow electrodes, that's where the ultra-high vacuum is. And all the magnets are in the liquid helium bath, which is external to that. So this gray tube separates the vacuum from the cryogenic environment. Right? So it's all going on inside those yellow things. What we do is make the antihydrogen from the charged particles, hold it with this big magnetic field made by the red and the green coils, and then to show that we had it, we shut those coils off very quickly. Right? We throw it out to then look for the annihilation at the time when we threw it out. That's how you show the world that you've trapped antihydrogen. You have to trap it and then throw it away. You decide when it goes, and you look for the annihilation signal.
When I read the paper, to me, I thought what the magic was seemed to be your ability to lose that magnetic field quickly. Was that the magic to actually being able to detect the so not the timing, but
you're absolutely right. Okay, there are many important elements. Yeah. That's one of them. Okay. You're looking for one atom at a time when you start this business, right? This is what we call rare event physics. Remember, a gram of hydrogen has 10 to the 23rd atoms. We're looking for one. And right. When you're looking for one, you want to look in a time window that's as small as possible. And we achieve that by learning how to shut these magnets off very quickly. In fact, compared to our competitors, we're orders of magnitude faster. And that was one of the very key ingredients to doing this. So you read very carefully. That's well caught.
I tried. So I suppose you might want to patent this, right? It's published. It might be too late to patent it. But if God forbid, go ahead.
We don't think like that. We're okay. On to the next thing, and it's about the science.
Sure.
I don't know who would want to do this. It's crazy.
Yeah, you guys, right? Yeah. I guess you guys want to do it. I understand that CERN is probably the only place that can create that field of cold anti-protons that is good enough for this kind of experiment. And you guys have the best, fastest magnets the magnets that shut off the fastest. I'm trying to visualize here now. You've got your beam coming in on one side, your beam of positrons and your antiprotons coming from the other side. How far have these subatomic particles traveled at CERN? I mean, it's a big loop. Do you absolutely need a 10-mile circle? Is it 10 miles circumference?
Okay, this is a common misconception that we need to clear up. We don't use the LHC, the big machine, in any way for this research. In fact, this research predates the LHC by 20 years. We're, again, working at low energies. We have a dedicated machine. It's called the antiproton decelerator. Again, we're trying to slow them down. And it has nothing at all to do with the LHC. That was a perversion of Dan Brown in the book and the movie. But we don't need the LHC.
Did they come and consult with you?
I think he talked to somebody. It wasn't me.
Okay. I've interviewed... go ahead.
He wouldn't have gotten so terribly wrong if he had talked to me.
I talked to Jack Horner's Futures in Biotech episode, and he was the scientist that was Michael Crichton modeled Jurassic Park on. So, he got it pretty right, I guess. Although a lot of the genetics, there was a lot of leap of what can be done and can't be done yet. But I suppose eventually we'll be able to do that kind of stuff. Okay, so you've described your anti-hydrogen trap, how it works. Maybe you could run us through an experiment, on a day-to-day basis. So how often can you do this? Is there a lot of preparation? Maybe you could just tell us how the first, I mean, the 2010 versus the April publication. Was it April?
June, the second one.
June, right. Trapping it for 1,000 seconds. So the first.
That's right.
Okay, maybe you could describe quickly the scale of both experiments and how they differ.
Okay, let's go through a typical day. The machine operates 24 hours a day to produce antiprotons. There are 3 experiments that run 8 hours a day each, so we're sharing the beam with 2 other experiments, both of whom are competitors, by the way. This is a very interesting environment. There's only one place in the world where you can do this type of research, and your arch rival competitor is 5 meters from you. Right, so this is why we drink.
Water.
So, yeah. Typically, you show up for the beginning of the shift. The first thing is setting up everything, steering the beam, the antiproton beam to the right place. We have what we call baseline measurements we do every day just to make sure that everything is working. This is an incredibly complicated experiment. There are many, many things that have to work at once to get this to work. And so the baselines take some time, a couple hours perhaps. And then you can get to the point where you're actually mixing antiprotons with positrons and looking for trapped antihydrogen. One attempt to do that, in other words, mixing one cloud of antiprotons with one cloud of positrons, trying to trap them and releasing them to see if there was something there, takes about 20 minutes of real time. Okay? In an 8-hour shift, we can do about 20 of those. There are some other limitations. When we shut these magnets off very quickly, for example, we have to wait for them to cool down again. We dump some energy into them, and they need to be stable again. The trap itself heats up a bit, so we have to wait for it to cool down. So typically, a typical day like that, if we're just looking for trapping and trying to collect statistics, we'll do 20 of those measurements in a day, and with interspersed checks to make sure that everything is working well. But that's a typical day. The whole collaboration runs 24 hours a day. When we don't have our 8 hours of antiproton beam, we're working with positrons and electrons to try to improve things. One of the key parameters, for example, is what's the temperature of the positron cloud. The lower you can get that, the more antihydrogen you can trap. So in 2010, we were just learning how to do this experiment consistently and repeating it many, many times, looking for events. And back then, we got about 1 antihydrogen trapped in every 8 attempts. 8 of those attempts that take 20 minutes each. And a lot of the time is spent just making sure that things are consistent, that you have the same parameters every time. So, and again, the whole point of the 2010 measurement was just to demonstrate that this was possible at all, right? So we do these attempts every day, and we throw the antihydrogen out almost immediately after it's produced and caught, right? You're looking for something rare, so you start at time 0. You don't wait 15 minutes to see if it's still there. You throw it out as soon as you think it might have been there. And that was the 2010 result. The number for the time antihydrogen was trapped was 172 milliseconds. A lot of people interpreted that as being some sort of a limit, but it wasn't. It was as fast as we could do the experiment and throw these things out.
And well, it's not that actually short, right? But so I guess it's when you guys decided to flip the switch, right? It was arbitrary. It was about how efficiently we can reproduce the formation of assembled antihydrogen. And 1 out of 8 isn't bad. I mean, that means every 20 minutes, 2.5 hours, and you've got an antihydrogen. How many would you get per batch? Is it like you detect 1 per batch, or
no? We detect 1 in every 8 batches that we do. Right, that was the original efficiency.
One anti-atom.
1 anti-atom at a time. Yeah. It was a long time before we were sure we had trapped 2 at once, for example.
I noticed in the image of the antimatter trap, and I'll put it up on futuresinbiotech.com, or I'll link to it, actually. I'll link to the original source. That way there's no proprietary anything. It looks like was it the electrodes here? I'm pulling it up. Yeah, so the electrodes are in the inside and the annihilation detector are in the outside.
That's right.
Is it just because the energy is so strong that you can detect it through the electrodes?
Yeah, what happens, again, the E equals mc squared thing, the antiproton annihilates with a proton, makes energy, but that energy converts almost immediately into mass again. And the mass in this case are particles, subatomic particles called pions, and they come screaming out of the apparatus at close to light speed. So the annihilation detector can see them even though it's outside the magnets and the cryostat, the cold chamber. It's a very important aspect of our experiment that the magnets don't have a lot of mass. They don't have a lot of stuff that can scatter the particles that come out, so that we can find exactly where the antiproton annihilate. It's very important that we don't just measure that something happened, we measure where it happened. That's also unique about alpha. We have a position-sensitive capability. We know exactly where this annihilation happened on the wall of the apparatus. So, in fact, the technique that we got from Brookhaven is sort of tailor-made to us. These are magnets that have almost no metal support structure so that we don't scatter a lot of the things that we're trying to detect.
I know people are shouting at me here and through their iPods. I'm sure they're shouting, what are pions? So how does the anti-hydrogen, this is fun, this is great stuff. How does the anti-hydrogen then annihilate itself? Does it require an anti-hydrogen, or does it just require an anti-proton? An anti-proton and an anti-electron? Do they split and then annihilate? And then how does that high energy then convert back to pions?
Okay. Both particles annihilate. The positron will annihilate on an electron. Again, in the metallic, the yellow things in your diagram, those are the electrodes. They're made of aluminum with some gold. So the positron will capture an electron from an atom on the surface and annihilate. For the antiproton to annihilate, it needs to meet some quarks, right? So the antiproton is made of 3 quarks, antiquarks. It needs to meet some regular quarks to annihilate. So it has to go into an atomic nucleus to annihilate. So now you have this antiproton, the quarks and antiquarks annihilating. They can produce energy. They can think of it instantaneously. They disappear into energy. But then this energy quickly manifests itself again as other types of matter. Now, we have enough mass, just enough mass from one antiproton and one proton. Because of Einstein, we can only make things that are lighter, particles that are lighter than the proton and the antiproton. There's not enough energy for a proton or an antiproton to emerge again. That's extremely unlikely. So the quarks appear again as mesons. Mesons are particles that have 2 quarks instead of 3.
All right.
The proton, the antiproton, and proton are baryons. They have 3 quarks. Mesons are things with quark and an antiquark. So this makes some number of these pi mesons. They can be positive, negative, or neutral, and they just come screaming out of the apparatus. They weigh about 100 MeV, sort of a tenth, roughly, of what a proton or antiproton weighs. So you need a few of them, and they come out with highly relativistic energies. So the charged ones are the ones that we can detect. And you can just think of this as, 4 things flying out from a point. Right? That's the event, typical event. It could be 2, it could be 3, it could be 6. But they fly out from a point on the surface of those electrodes. What the detector does is there are 3 layers of it. If one of those things interacts in all 3 layers, you can find out which way it was headed. If you have two of them, you can project back to see if they intersect someplace on the wall of your thing. You have three, it's even better. So we call that thing a vertex, right? It's the point where these tracks from the charged pions emerge and indicate that an antiproton annihilated. So we can see in time and space where our antihydrogen came out.
Is it a problem to gain normalize this? How do you, like, and does it destroy? I mean, I guess not, right? It doesn't destroy the materials, right? The level of energy.
In my dreams, we would have enough antimatter to destroy something. No, this is violent on a microscopic scale. It's the most violent thing you can do on a per particle basis, right? Annihilating antimatter. But it's, remember, we're doing one atom at a time. You couldn't detect one atom of hydrogen. You'd have no way to do that. But because it's antimatter, you get to see the stuff. So it's completely trivial amounts of energy on a macroscopic scale, but to us, it's an event with a really loud bang.
It's this amazing stuff. I think we have a title, Quark Anti-Quark, but we often try to find material in the interview to give it a title. But what I'd like to do now is possibly go on a tour of your laboratory. We've got the website. If Liz can get the Alpha Experiment Facility and Professor Jeffrey Hangst website, we could go through some of these photos. It's from the same page as the AntiMatter Trap. And then after, we can go to the, would probably discuss, the future experiment, what you're going to do and how you're going to measure the properties of anti-hydrogen. All right,
okay.
So here we've got some, wow, okay, that's the alpha.
Yeah, that's it. All right, so we'll start in the sort of the middle at the bottom. You see a silvery looking large cylinder.
Mm-hmm.
It's kind of corrugated. No, not there. Close to there, yes. So that's the main magnet. That's a big solenoid magnet. It has a constant magnetic field, again, like an MRI magnet. The antiprotons come into that thing at the bottom right. There's a beam line from the antiproton decelerator, and we catch the antiprotons inside that magnet. To the left and sort of up from that cylinder, you see a band of yellow. Not there, the next one, further there, exactly. That's where the positrons are created and stored. That's another magnet. Just to the left of there is the radioactive source that emits the positrons. So that's what we call the positron accumulator. That just sits there all day long and can accumulate positrons that are being emitted from a radioactive source. So we store up typically, say, 10 million positrons and then shoot them into that original domain magnet. And that's where we create and trap the antihydrogen. Those yellow bars that you see, the ones you pointed to, those are carrying the current that goes to the superconducting magnets that make up the atom trap. The atom trap uses 1,000 amps in round numbers, and that takes a sort of 50 millimeter by 10 millimeters of copper, solid copper bar, to get that current into the cryostat where the liquid helium in the superconductor is. Interesting thing about superconductivity, that 50 millimeter by 10 millimeter copper bar becomes a 1 millimeter diameter superconductor when it's inside the liquid helium. It's really an amazing process, superconductivity. So those are carrying the high current that make up the magnetic field to hold on to the antihydrogen. And you can actually, those cylinders, you can see me in the back, I'm standing on a dewar of liquid helium. Each one of those has 500 liters of liquid helium. We use 3 or 4 of those every day. So one great thing about being at CERN is that the liquid helium is for free. We would use something like $1 million worth of liquid helium every year if we had to pay for it. So we have to transfer the liquid from those dewars into the large system sort of 3 or 4 times a day. And that's what we're getting ready to do there. And if you
don't
see
have a feed line, it'd be nice if you had a feed line and you could just feed it in.
Yeah,
right?
we're hoping now that, by the way, CERN has just agreed to build us a new machine. In fact, there was a press release, I think, 2 days ago about this, that will slow the antiprotons down even further so that we can use them much more efficiently. So they're making a big new investment in our program, which we're very happy about. And hopefully that investment will include something like a transfer line for liquid helium, for example. So they're very happy with what we've done lately and are working to invest to make sure that we can continue to the next step.
Yeah,
there you see, this is the ground level view of the thing. Whoops.
Did Harvard donate the A-Trap?
Harvard is the competitor. The spokesperson of A-Trap is a Harvard professor. So you can see that is the A-Trap experiment. They have a different geometry, but they're right behind us, right, really just 2 meters away. So this is an interesting working environment.
That's
okay,
fantastic.
So if you're looking at the ground level view now, the silvery box to the right with the yellow signs, the radiation sign, that's where the positrons come out. There's a radioactive source. It's sodium-22, and it's in a big lead shield, which is inside that box. And then you can kind of see the beam line running to the left from the radiation sign. That's where the positrons go into the magnet, which has the yellow band on the end. So that's just the positron end that you're looking at, and you're seeing a bunch of electronics racks that are used to control this thing.
Let's go to the next photo. It'll be really hard to describe what we're looking at, to the listening audience. But I really encourage you to go to the link. We'll provide the link on twit.tv/fib and on futuresinbiotech.com. We're looking, just to give you a brief idea of what we're looking at here. We're looking at what looks like a deep underground laboratory with 100 million miles of wire. Or no, maybe 1,000 miles of wire, maybe more, and some very large computer apparatuses with magnets and struts and all kinds of really things. Just to give you guys an idea of what we're looking at, but Professor Hangst can perhaps explain this next slide.
Okay, so what we're looking at here is we're looking at the point where the antiprotons go into the device. So there's kind of a yellowish disc, which is the end of the big magnet. I don't know if you can see that. Yeah, exactly there. So that's the entrance to the big magnet. To the left of there is the beam line from the antiproton decelerator. And what you're looking at is those ribbon cables coming out are the cables for the annihilation detector. It has about 8,000 channels of silicon strip detector that are looking at the antiproton annihilations. That's the rest of it is sort of vacuum equipment and electronics for reading out the detector.
What is the mechanism for the vacuum? And that still fascinates me. I don't know why the vacuum fascinates me, but it's probably for my work on electron microscopy. Is it like an oil pump, and then, or is it is there some kind of ion trapping? How does that? Maybe you can show us. Go ahead.
People would hurt you if you tried to get an oil pump close to this device.
I suspect.
The basic workhorse is an ion pump. Right? You have to do some roughing. You have to, get the gross air out. But for the ultra high vacuum, in fact, if you go back to that last picture, I don't know if you can get that up again. You might be able to see the ion pump, which is what it does is, it's dead center at the bottom. Exactly. That's an ion pump. There's a big magnetic field there, and a system to ionize things and then trap them so that they can't get out again. Right. So that That's what we call an ion pump. That's good in sort of rough numbers down to 10 to the minus 11 torr. But the thing that really separates a device like ours and anyone who's working with cryogenic vacuum systems is that the walls of the apparatus pump for you, because in a vacuum you have molecules bouncing off the walls. If the walls are really cold, the things that are bouncing off the walls cool down, and eventually they just stick to the wall. That's called cryopumping. And in fact, the vacuum in this apparatus is too good to measure. There's no gauge that can measure the vacuum. In fact, we actually use the antimatter to estimate how much stuff is there, right? We can see how often we lose an antiproton because it collides with some matter, and then you can estimate the vacuum. But it's better than you can measure. All so right. This is one of our students there is getting ready to transfer liquid helium from the dewar on the left into the main storage dewar.
Of course, it's the students, right?
I do this.
You did it for years.
This too.
Oh,
no,
okay.
I did it yesterday. It happens all the time.
Lead by example.
I like the gear too. It's fun.
Let's go to, there's a, do we want to, okay. There's a gauge there.
Yeah, that's just a pressure gauge. What you're seeing here, the thing with the frost on it, that's where the liquid helium goes into the apparatus, and where the gas that's produced, when the helium evaporates, comes out. So that gauge is just measuring the helium pressure at the top of that. We call it the tower. There's just a volume of liquid helium in there that maintains a buffer above the superconducting magnets so that they never get exposed. They're always in a bath of liquid helium. And we're pumping liquid into that device all the time to keep the thing cold. It's a funny story, when the Angels and Demons thing came out, the Sony Pictures sent a whole entourage of people, including Tom Hanks and Ron Howard, to come and talk to us and do interviews and stuff. And they brought a bunch of journalists with them. There was the History Channel, the Science Channel, and the people from Entertainment Tonight came in and looked at our lab. They wanted to film something, but they decided it was just too crappy to be on Entertainment Tonight. It didn't look like Star Trek or whatever they thought it should look like. And they just kind of turned on their spike heels and went out.
I'm thinking about, I'm looking at this lab, and it would be really fun to visit. I'm sure I can't speak for everyone, but a large percentage of our audience would have a blast playing with some of the gear that you've got and getting trained. What a fantastic setup. I mean, you have more monitors than anybody. This is cool. Okay, so go with this, please.
Yeah, so this is the control room. So when the antiproton is there, you can't be down on the level where the experiment is. So we run everything remotely. And this is one set of monitors that we use. This is the main set for controlling what goes on. And so there are many screens to cover all the gear that's going on. The blue thing in the middle is what we call, it's an indicator of what we call the sequencer. This experiment requires many steps of changing the voltages on the electrodes, ramping the magnetic fields up and down, and that device is sort of flashing LEDs to show us what's going on. The screen, the sort of greenish one with the horizontal line, that one exactly, that shows the voltages that are being applied to the electrodes, that the yellow things in the line. So those are bouncing up and down and to move particles around, to mix them together and so on. So this is typically when we're running an antiproton shift, we're 4 or 5 people to keep it all running and to analyze data as we're on shift, but it all goes on here.
Let's go to the next one if we can. This looks like a mock-up of the, all right. Is Liz there? Oh, there. Cool. We're looking at what looks like a green and yellow tube with circuit boards up and down each side. What is this?
This is the annihilation detector. Those are circuit boards. You're looking at the sort of the back of the outside of the third layer. So each one of those rectangular modules has silicon strips on it. It's kind of like a super CCD camera. It has segmented patches of silicon, and when a charged particle flies through there, it charges up the local area. And this device stores the charge and then reads it out and says where it was in position. So there are strips along the length on one side of the device and strips perpendicular to those on the other side. So when a particle flies through and charges this thing, you get an XY position, okay? So you can see each one of those rectangular things is one of the modules in that cutaway view that you showed earlier. And there are two more layers of this stuff inside. Then the electronics are the readout, you know, that you sample these things in a sequence. So there are specifically designed ICs sitting on the green circuit boards to read out this device very quickly. So anytime an antiproton hits inside this device and the pions come flying through, this thing triggers. It says, okay, read me out. And you get the position information from where the charged particles hit. And then we have, of course, very sophisticated algorithms to convert these signals into real positions and real tracks of the charged things that come out of there.
Right, so it's not just XY, but like you can follow its movement through the different layers.
Yeah, you for example, one particle coming through radially will give 3 hits, one in each layer. And you draw a line through those hits, project it back to the inside, and it's pointing at the vertex, the place where the antiproton annihilated. If you have 2 of those things, you can find an intersection and say, okay, here was an antiproton annihilated. There's some background, what we call unwanted signal, and that's mostly from cosmic rays that are coming from outer space, but they just go vertically through the detector, right? They're coming from overhead. They travel in straight lines through this detector, and you can use the topology of the reconstruction of these things to distinguish them. That's another very important feature. When you're looking for something rare, you want to be able to distinguish it from the background. The background in this case is cosmic rays. You already very astutely identified one way to minimize that is to have this thing shut off very quickly, right? So cosmic rays come at some fixed rate, roughly. If you can narrow the search, you have much less chance of seeing a cosmic ray in the time that you want to look for your antihydrogen. The other way you do it is through the geometry. Cosmic rays go in straight lines. Antihydrogen annihilates into a couple or more tracks. They just look very different.
You said that the cosmic rays come from above only. Is the world, the Earth, big enough to filter out all of the ones coming from below?
But they're coming from everywhere.
Okay.
There's an angular distribution that's mostly overhead, but it has some characteristic angle. So they're not precisely from overhead, but the distribution of them in space is well studied. So you can use that, for example, to see where is up in your detector.
Okay, so it's not just... Sorry. We've got a little bit of lag. It's not just from above, but it's from a specific area of space. Have you gone outside and said, that part of space is producing my noise?
And no, it's very general. They're coming from everywhere.
Let's go to the next photo. It looks like a electron density map of a protein called GROEL from the what you call a transverse section of it, cross section. What is this?
Okay. Yeah, this is cool. Okay, what this is, take the one on the left first. Remember how I told you that the antimatter, when it comes out, it annihilates on the inner wall of those electrodes. Okay, that's a cylindrical surface. So what we've done here is just allowed a lot of antiprotons to annihilate and found their positions. So this is XY. This is the kind of a cross-section cut through the experiment, and then we project it along the axis to get them all. So what you're seeing is the yellow band is the inside cylinder of the electrodes, the inside surface of the cylindrical electrodes. That's where the antimatter is annihilating. It's not perfectly sharp because there's some resolution of this detector, right? It has an inherent fuzziness because these things scatter when they go out. So, but you can still see they're clearly centered on the inside diameter of the trap. And the other one is just a different projection of the same data. The Z direction, or Z direction for Americans, is along the long axis of the trap, and phi is the angle around the circumference, right? So in this case, there were two circular bands of antiprotons annihilating, and this has to do with the symmetry of the magnetic field that's applied to the. These are charged particles annihilating. These are antiprotons, not antihydrogen. This is just to show you that we're very sensitive to the position of these things, and we can count them one at a time.
So you've given us a tour of the lab, and we now understand the technology and the science that leads to the production of antihydrogens. When, maybe give us a timeline. What's the next step? How are you going to capture this? Are you going to do like chemistry on it? Or when do you foresee doing chemistry on the hydrogen?
That would be really cool, but not in my lifetime. Again, we're still trapping, 1, 2, 3 atoms at a time, and to give you an idea, the volume of the trap is sort of 20 centimeters long by 5 centimeters in diameter. So you'll never do chemistry with 3 atoms in that volume. They just don't talk. We think we can get to sort of hundreds of atoms once we settle down and really build the next device, which is what we're in the process of doing. In the meantime, what's this all about? It's kind of cool. Okay, well, I can make anti-atoms. I can hold on to them. Why? Well, what we want to do is study the structure of the anti-atoms. We want to see, in particular, if the spectrum of antihydrogen is the same as that of hydrogen. Okay? Antihydrogen is the only antimatter atom we can make, but that's not so bad because hydrogen is the thing we understand best in the universe. Right? We know everything about the hydrogen atom that can be measured. Just to give you an example, the sort of cartoon picture of an atom is we have a proton and an electron going around in a circular orbit, right? And the ground state, we call n equals 1, is the lowest energy. You can use a laser to excite that electron up to the next orbit, to n equals 2. N equals 1 to n equals 2, the first transition in hydrogen. The frequency of the light for that transition is known to a few parts in 10 to the 14. Okay? So 0.1402 is the precision of that measurement. It's the kind of the second best number that we know in physics. If you want accuracy in physics, you talk to an atomic physicist. At CERN, people are good at smashing things together to make new things, but it's not exact science. It's spectacular, but it's not precise. Precision is in atomic physics. So the reason we're doing what we're doing is because we understand hydrogen so well. So the laws of nature as we know them today predict that hydrogen and antihydrogen must behave in exactly the same way. And that's what we'd like to test experimentally. This is a very, very deep implications for what are the structure of space and time, right? What's the basic symmetry of how things are put together? So our next task is to shine light on antihydrogen, quite literally. We want to interact with it with electromagnetic radiation. And two obvious choices, lasers and microwaves, right? Because the spectra of hydrogen have been studied for 100 years, and it's just one of the things we really understand. Mm-hmm. So what we're doing right now in the lab in the last few months is trying to catch more antihydrogen, first of all, and also to shine microwaves on it. The current alpha apparatus doesn't allow us to shoot lasers in there. So we're trying to put microwaves in. And here's a really elegant little experiment. Remember I told you the antihydrogen was like a magnetic compass needle, right? Mm-hmm. When it's in the trap, it's pointing in a given direction along the magnetic field. If you hit that compass needle with just the right frequency of microwaves, it'll flip to the other direction. It's just a 180-degree flip of that little compass needle. And when it does that, it goes from wanting to stay in the trap to wanting to go out of the trap as quickly as possible. So you can make what we call a resonant interaction, right? It's exactly the right frequency, and that frequency would be the same in hydrogen. And if you hit it just right, your antimatter comes out, right? And this is an experiment, because it's antimatter, we could do with a single atom, because we can see that single atom when it comes out. We've made all of our history of working with antimatter has allowed us to detect very, very rare things, one atom. So even though we don't have many, the fact that we can interact with it for a long time, we didn't really talk about that, but this 1,000 seconds of interaction has convinced us that we have a good chance of doing the first real measurement on the internal structure of an antiatom. And that's what we're working around the clock to do right now. We have until the 21st of November, is the end of the run for this year, to try to demonstrate this particular interaction. And if that happens, then you'll invite me back.
Definitely. No, absolutely. We'll talk about it. I'm thinking, I'm trying to understand here, because these are anti-atoms, you're able and you have the ability to detect them through annihilation. You've got a unique rare event situation, if that's what I understand, ability to measure and quantify stuff that just in the normal universe of matter was not possible.
It's not that it's not possible in the normal universe of matter. The things that we're trying to measure have been measured very, very accurately in hydrogen. But you can get hydrogen from a gas bottle, right? You can have 10 to the 23rd atoms of hydrogen.
Oh, sure.
For free. So what's unique about this is that you can do it with a single atom of antimatter. You could never imagine making this measurement on hydrogen with a single atom. But it's been done with many, many atoms, so we don't care. We just want to compare to what's already been done.
Are you expecting, have you guys made bets, expecting perfect symmetry, or is the nature of the Big Bang, which produced matter versus, or got rid of antimatter, and that left turn that we talked about, that the universe at the Big Bang made a big left turn and made matter versus antimatter, or annihilated most of the antimatter, are you, because of that left turn, are you expecting the symmetry to be a little bit off?
That's what's so cool. Nobody knows, right? I usually say that all these symmetries are 100% good until they're not. And you just don't know if you're looking at the system that will show the symmetry break or not. That's why you keep looking, right? Nobody has found this yet. Where is it? It could be an antihydrogen, maybe not. Maybe antihydrogen is exactly the same as hydrogen. But it's a unique system. The thing that's so interesting here is that the precision you can achieve is so much more than you could ever do in a high-energy physics experiment. So we're kind of morally obligated to look at this.
You're at the limits of human knowledge. You're at a frontier of understanding our universe. This has been an amazing honor. I think we'll leave it at that, and we'll wait for the December interview after the big ceremony.
Okay.
Are the ceremonies in January? I don't want to jinx it. I'm just gonna
no promises. No promises there.
But I also don't want to jinx the big event, the big meeting, the big scientific. Because I think you guys are on track. This is really great stuff. Not only is it great, but it's so fundamental, and it really spurs the imagination. We haven't even gotten to the sci-fi stuff and whether or not, I guess we lightly covered it. But let's stick to the real science, because this is real. You're not living in a fictitious world. This is real world stuff. And just for those people who wanted to see, there's the 14 zeros. I'm trying to do this in reverse. Precision of physics. I don't even know what the units are. I mean, I guess it's quite irrelevant without the units. But what are the units on this? Millivolts?
That's a percentage, right? That's a dimensionless sum. It's a delta frequency over frequency. Right?
Delta frequency over frequency. I'm jotting this down. I got my notes here. Thank you very much for coming on the show. This has been a true honor.
My pleasure.
And I think we learned a lot. I certainly did. And it's really fun to get a first-hand account. I wish you well. I wish you best of luck. We'll be following the story to find out whether the universe is perfectly symmetrical, whether or not this level of technology and understanding hydrogen will answer that symmetry question. And I hope in our lifetime we'll find out if the Big Bang took a left turn, or, there's... these are just great questions. I look forward to reading more and following your story. Thank you very much for coming on the show.
Thank you. No matter what happens, I'm having a lot of fun. And imagine getting paid for this. Take care.
All right. Thank you. Yeah, getting paid for science is amazing. It's a very lucky thing to do.
It is. Thanks a lot, Mark.
Have a great day.
All right, you too. Bye-bye.
Bye-bye. Or good night. Thank you for coming on so late.
Yeah, it's okay. We don't sleep.
We'll send you some contact information. Yeah, I know. I guess you don't sleep. It's day or night. When you're in the basement, it's day or night. Doesn't matter. We'll contact you. I'll send you some links of when it's posted. It should be posted later today, and I'll post those images, the links to the images for the audience to go in and follow the story again. Thanks again.
Okay, it's people are welcome to write to me. I try to answer questions, however bizarre they may be. So. Don't hesitate.
All right. Well, they can write to you. They'll find your email. There's thousands of people, so they can find your email at this link that we're going to put. So they'll have to do a little homework to get your email. All right. Thank you very much.
All right, Mike. Thanks. Good night.
Bye-bye. Good night. I'd also like to thank Liz Romero for handling the video and audio streaming and the production today. She did a great job, and man, I think one of the fun parts about it is you were able to put the mouse cursor right over the device that he was explaining. And once people go and look at the video of this, they're going to see that it's the most complex mesh of wires and magnets and cryotubes. And so great job on that, Liz. That was pretty amazing.
Yeah, no, next time we'll find some way to IM. So therefore I'm like, wait, is it the next one or the next one image I'm supposed to bring up? So we'll find a way to communicate during the show that makes us look more professional so they don't know about it.
Oh, you did. You nailed it. You nailed it. This is really great. So I think as is, it's a great production workflow. I'd also like to thank our chief twit, Leo Laporte, and the rest of the team in Petaluma, California that make this possible. Any comments or suggestions, you can reach me at Marc, M-A-R-C, at twit.tv or on Twitter at Marc Pelletier, M-A-R-C, P-L-L-E-T-I-E-R. I'd also like to mention National Science Foundation has put out a new science radio network, and Futures in Biotech is featured on it. If you want to check out some great science shows, the scientific community really, this helps them. So go check out the National Science Foundation's Science 360 station. And that's pretty much it. So for Futures in Biotech, I'm Marc Pelletier.